Welcome to the 2021 Georgia Tech Design Build Fly video report. My name is Antoine Paletta, the Chief Engineer, and together with our project manager Tristan Huang, we will be presenting our entry into the 2021 competition, SR-71 Black Buzz. Our aircraft is piloted by Gautam, and our team is split into 5 subteams as shown in this slide. The first step in the design process was to determine key scoring trades. 2 opposing design goals were given. The ground mission and mission 3 encourage fewer shipping containers, while mission 2 encourages many shipping containers. The scoring analysis showed that minimizing the number of containers and maximizing the sensor's weight would maximize the total mission score. The next plot shows the mission 3 raw score as a function of sensor length and sensor wing width, which correlates to its weight. The team settled on the design point and scoring targets shown to balance system reliability with achieving a high competition score. Black Buzz is a conventional configuration aircraft design with a high-mounted wing to allow space for payload bay doors. A T-tail was chosen to minimize the chance of an impact to the elevators during a sensor recovery. Black Buzz's wing spans 5 feet and the reference area is 7 square feet, giving it a relatively low aspect ratio of 3.57. The root chord of 20 inches tapers down to 9 inches at the tip to achieve a more optimal lift distribution. The fuselage was designed around the sensor's dimensions, and as such, the payload bay is 11 inches wide and over 3 feet long, bringing the aircraft's total length to 79.3 inches. The aircraft uses 2 separate receiver circuits for the main control surfaces and the subsystems to reduce any potential interference with the flight controls. The main receiver actuates the nose gear, rudder, elevators, flaperons, and motor. The elevator is split and operated by 2 different servos for added redundancy, and flaperons are used to reduce landing speeds at high wing loading. The subsystem receiver uses a smaller secondary battery and ESC to power the spooling mechanism, claw mechanism, cable guide arm, and payload bay door servos.
This is the aircraft in its Mission 1 configuration with no payload. It's the lightest at 11.5 pounds gross weight and a wing loading of 1.6 pounds per square foot. Its low drag design allows it to reach a top speed of 138 feet per second. The Mission 2 configuration, weighted down by the sensor, container, and recovery mechanism, sits at a 15.3 pound gross weight and has a higher wing loading of 2.2 pounds per square foot. The extra weight minimally impacts the top speed at 134 feet per second. Finally, the Mission 3 configuration is the heaviest, due to the sensor and an extra battery, weighing 16.2 pounds with the heaviest wing loading of 2.3 pounds per square foot. The extra drag from the towed sensor and reduced throttle due to the battery energy limit lowers the top speed to 89 feet per second. Modal calc was used to predict the performance for different propulsion system configurations. Thrust versus velocity curves for each configuration were analyzed to choose the system providing the best balance of thrust at takeoff and cruise. The selected configuration consisted of a 17x12 propeller, a Hacker A60 5XS brushless motor, and a Castle Phoenix 100 amp ESC. LiPo batteries have higher energy densities than other battery types, so 2 Scorpion 6L 4500 mAh LiPo batteries were used in parallel to increase capacity. The continuous current draw was limited to 50 amps for Mission 3 to provide 10 minutes of endurance in addition to takeoff and landing. Aircraft performance for each mission was predicted using a 6 degree of freedom trajectory optimization program. Lift and drag assumptions were made based on completed aerodynamic analysis for each mission configuration, while throttle setting and roll angle were allowed to control the aircraft's acceleration. Constraints were applied based on assumed load factor limits for towed sensor flights, while an assumed wind speed was used based on Tucson weather data. The model predicts lap times for each mission, which were compared to actual lap times from flight testing. The predicted Mission 1 lap time was 26.9 seconds, while the actual lap time took slightly longer at 28.2 seconds. For Mission 2, the predicted time was faster than the actual time at 29.3 seconds and 34.2 seconds respectively. The actual Mission 3 lap time was 57.4 seconds, slower than the predicted 43.5 seconds due to extra drag from the sensor and payload bay doors. The actual number of laps flown for this mission was 10, less than the predicted 13.
Technical inspection is an important part of a DVF competition, and here you can see that the completed aircraft matches the CAD assembly from the report. Next, the ground mission is performed. Here you can see us demonstrating the functionality of all the subsystems, including payload bay door opening, sensor deployment, sensor light activation with a signal sent through the electrical tow cable, sensor light blinking in a pattern specified by our team, then sensor recovery into the aircraft, sensor light deactivation, and finally closing of the payload bay doors. Here is Black Buzz taking off during flight testing. We mounted an action camera to the tail to provide an onboard perspective. Here is Black Buzz performing a successful landing after a simulated Mission 3 flight. The sensor is inside of the closed payload bay before the landing. To deploy the sensor, the pilot flies Black Buzz in a straight line after opening the payload bay doors. The sensor slides out of the payload bay, after which the drag on it unspools the tow cable. We found that pitching the aircraft up helps make deployment more consistent during flight testing. Here you can see the sensor in stable flight while towed behind Black Buzz. The annular tail design helps keep it aerodynamically stable and the tow cable taut, while its wings generate enough lift to support its own weight and allow it to fly behind the aircraft instead of below it, reducing oscillatory coupling dynamics. The zoomed-in view shows the sensor lights functioning in flight during a sunny day in Georgia. Here, you can see a sensor recovery pass where the pilot flies in a straight line at high speed while the payload bay doors are opened and the sensor is spooled in. The main challenge with recovery is the high-frequency oscillations that occur when the tow cable is short. These were mitigated by slowing the spooling rate just before the recovery. Thanks for watching.